In this video, we'll be taking a look at the Lesson 7 packet, specifically pages 1 through 4. So this is part 1 of Lesson 7. Number 1, type each of the following into your interactions window and press enter. What does each expression evaluate to? So in letter A, we're typing parentheses, less than, space 3, space 4, close parentheses, and when I hit enter, that evaluates to true. So that's the answer for 1A. 1B, less than for 3, close parentheses, evaluates to false. And letter C, equals for 3, evaluates to false. Back in the packet, you can write down those answers for 1A, 1B, 1C. And number 2, in number 1, we get outputs that are not numbers, strings, or images. So what type of data is it? A new type of data that we have now are called Booleans. Booleans are answers to a yes or no question. So when we type in letter A, for example, we're really asking the computer, is 3 less than 4? Since the answer is yes, it returns true. Letter B, we're really asking the computer, is 4 less than 3? Since the answer is no, that returns false. And in letter C, we're asking the computer, is 4 equal to 3? Since the answer is no, that's a false. So Booleans are answers to a yes or no question. But there's only 2 things a Boolean can be. Boolean values can only evaluate to true or false. It's either one or the other. There are no other options for a Boolean. So let's take a look at number 3. Convert each of the following math sentences into code, then state its Boolean value. So the first math sentence written in algebra is 10 equals 16.1. So when I write that in code, I know I need a parentheses. The function is equals. The first input is 10, the second input is 16.1. So that is written in code. I'll type that into the interactions window to evaluate it in a minute. Let's take a look at the third one together. 40 minus 1 is less than 90 times 2. So when we write that in code, the main function is less than. So that has to go first. The first input is whatever's on the left side of the less than symbol, which is a 40 minus 1. So written in code, 40 minus 1 looks like that. And the right side of the less than symbol is my second input, 90 times 2, which I have to write in correct code. So 90 times 2 written in code, and then close the whole line of code with a closing parentheses. So go ahead and go back and do these last 2 examples written in code. Pause the video now and do that on your own. Here's the correct code for the second and the fourth examples. Make sure in the last one that the equal sign is your main function. 0 is on the left side, so that's your first input. And the negative 5 plus 10 was on the right side, so that's your second input. That has to get written in correct code, which is shown here. And then, of course, we have a double closing parentheses at the end to close the whole line of code. So let's take a look at these and what they evaluate to in the interactions window. The first one I'll type in is 10 equals 16.1, which evaluates to false. The next one is negative 13 greater than 5? The answer is false. The third one is 40 minus 1 less than 90 times 2. And close the parentheses, that evaluates to true. And the fourth one, does 0 equal negative 5 plus 10? Close the parentheses, that evaluates to false. Make sure you have the correct Boolean values written down here. Remember, these were all yes or no questions. Is 10 equal to 16.1? The answer is no, so that's a false. Is negative 13 greater than 5? That's a no, so that's false, and so on. So these trues and falses are Boolean values. In number 4, complete the contracts below for less than, greater than, and equal to. So the less than function takes in 2 numbers as inputs and produces a Boolean, a true or false, as the output. That's also true for the greater than function. Takes in 2 numbers and produces a Boolean as an output. And the equals function. Is one number equal to another number? The answer is either going to be true or false, which is a Boolean. Okay, so we now have 4 types of data. We've been dealing with numbers, strings, images, a lot this unit, and now we're introduced to a Boolean. So those are our 4 types of data now. Let's take a look at page 2. On page 2, you should be on a computer if you can be, and type in this web address here very carefully, and let's go through page 2 together. Here is the program that the web address takes me to. It says click save. The file name can stay Cage. So it's already called Cage when you open it up. Go ahead and click save so you have it in your programs. Now click run. Some things to know about this program. I'm reading from your packet here. The first bullet point in the packet says, the window that pops up contains a butterfly named Sam. When the program begins, what are Sam's coordinates? So before I touch anything here, take a look up at the top at the x coordinate and the y coordinate. Those coordinates are representing the butterfly's position on the screen. So go ahead and write down that the beginning coordinates for Sam are 320, 240, and then you need parentheses around those as well. Back in the packet, let's keep reading these things to know about this program. Sam's yard, which are the boundaries of the screen, is 640 pixels wide by 480 pixels tall. Those are the same dimensions as our video game that we're creating. You can move Sam around using the arrow keys. Try it. Watch the x coordinate and y coordinate change at the top of the screen. As I press the arrow key up, I can see the y coordinate increasing, down, y coordinate decreases. Left, the y coordinate decreases, right, the y coordinate increases. Sam is free to fly around the yard, and the coordinates at the top of the screen update to tell you his location. What happens when you move Sam past the edges of the 640 by 480 yard? Does he stay on screen? So I'm basically going to test the boundaries here. I'm going to keep moving Sam left. Watch the x coordinate as it decreases, and take a look at what's happening. I'm holding down the left-hand key. Does he stay on the screen? No, he definitely does not on the left side of the screen. How about on the right side? Increasing x coordinate. Does he stay on the screen? No, he does not. How about if I get him back on the screen and try up? Does he stay on the screen when I move him up? Nope. And even though we can't see the bottom boundary of this screen, the blue boundary at the bottom, we can see that the y coordinate continues to decrease, and he is clearly off the screen here. So he's outside the boundaries of his yard. So the answer in the packet is no on this line. And now let's move on to actually read about what we're doing with this butterfly program. So read your task. Sam's mother tells him that it's okay for him to step outside of the yard, but only by a short distance. Specifically, she wants to make sure that she can always see at least a little piece of his wing. Sam is safe as long as part of his wing is on screen. Your task over the next couple pages will be to write the code that will keep Sam on screen and safe. Do a little bit of trial and error in your Cage program and fill in the blanks below. What is the first x coordinate on the left that you cannot see Sam on the screen? So let's test the limit on the left. Watch the x coordinate as it decreases. And I want you to tell me what's the first x coordinate that you cannot see Sam. So I can still see him, still see him, still see him, still see him, can't see him. So the first x coordinate that we can't see him is -50. Go ahead and write that down in the packet. The next question, what's the first x coordinate on the right that you cannot see Sam? So I'm moving Sam over to the right side. The x's are increasing. I can still see him, still see him, still see him, can't see him. So that x coordinate right there of 690 is your answer to the next question. So we have our answers to number 10 written down here. Let's take a look at number 11. Using the x coordinates from number 10, write 2 inequalities using less than or greater than that will keep Sam safe. So Sam's wing is still visible on the left as long as x is greater than -50. Sam's wing is still visible on the right as long as x is less than 690. So those are the 2 inequalities that will keep Sam safe on the left side and the right side of the screen. Next page. Unfortunately, right now there's nothing to keep Sam from leaving his yard. look at the code for the cage program and fill in the names for the 3 functions involved in this program. So when I open up the cage document, we can see all of the code here. There are 3 contracts written. There's a contract here for a function called safe_left, which has a hyphen and a question mark in there. Those are very important. There's another contract for a function called safe_right, and there's another contract for a function called onScreen with a question mark. So in our packet, let's go ahead and jot down the names of these functions and see what they do. So the safe_left function takes in Sam's x-coordinate and checks to see if Sam is safe on the left side of the screen. Safe_right takes in Sam's x-coordinate and checks to see if Sam is safe on the right side of the screen. And then the third function, the onScreen function, takes in Sam's x-coordinate and checks to see if at least some part of Sam is on the screen. So I want to clarify here, this makes sure that he's safe on the left side of the screen and safe on the right side of the screen. So in part 2 of the lesson 7 video, we'll be writing the code for the actual on-screen function, but this video we'll be writing the safe_left and safe_right code. So let's take a look at the safe_left design recipe. So the directions: use the design recipe to write a function safe_left, which takes in an x-coordinate and checks to see if it is greater than -50. So when we write our contract, the function name is safe_left. The domain, it says it takes in an x-coordinate. That's going to be a number. And it checks to see if the input is greater than -50. That's actually going to produce a true or a false. So the type of data that's in the range is a Boolean. So this is the first function that we're writing that uses a Boolean as the output. So for my purpose statement, I'm just simply going to restate the problem. The purpose of this function is it determines if a given number is greater than -50. So for our examples, we'll do one together, and then you'll be on your own for the second example. So for example, to check to see if Sam is safe on the left when he's at the coordinate, let's say +20, we want the computer to check to see, is 20 greater than -50? We don't actually have to evaluate whether 20 is greater than -50, but it is important when we're coding to think about what sort of a result would this produce, because usually we want our 2 examples to represent one true statement and one false statement, just so the computer is able to better understand our examples. So 20 is greater than -50 is a true statement. So when you go to do your second example, you can choose any number you want to go in place of this 20, but a good rule of thumb is to choose an x-coordinate that would produce a false statement. So go ahead and do the second example on your own. You can choose any number you want, but try and choose one that will produce a false outcome. Pause the video now. In my example, I use the x-coordinate of -200, which I know will not be on the screen. It will not be safe on the left side of the screen. So -200 being greater than -50 would produce a false outcome. When we circle the changeable parts of the code, let's use the variable x to represent the x-coordinate that we're using as our input. When we get down to the definition, let's use our examples to help us write the definition. The definition will look exactly like the example, so safe_left, but instead of using a specific number as an input, we're going to use our variable, which is x. What do we want the computer to do with the x? We want it to check to see, is x greater than -50? So that is our definition for the safe_left code. On the next page, we see that the directions are similar, but a little bit different now because this is our safe_right function. Use the design recipe to write a function safe_right, which takes in an x-coordinate and checks to see if it is less than 690. I want you to pause the video now and try the design recipe for safe_right on your own. So finish this page on your own to the best of your ability. Here's my design recipe for the safe_right function. I used one x-coordinate that would be a true output and one that would be a false output. We'll finish up this page in the next video.